Hi everyone, Assalamualaikum. My name is Muhammad Zaki Firdaus bin Ishaq. My metric number is 2025228.
Hi, my name is Noaidina binti Dusti and my metric number is 202444.
My name is Yasmin Noriana binti Rasid. My metric number is 203894.
Alright, so we are from group 7. We are going to present a topic which is called General Trends and Electronic Spectra of the Actinoids. And again, we are from group 7, consists of me, Zaki Firdaus, Ainina binti Dusti, and Yasmin Noriana binti Rasid. Next slide. So these are the table. This is the table contents, and these are the what we are going to present, starting from the introduction, properties, general trends, and electronic spectra. So this is the periodic table of elements. As you can see, the actinoid elements, we have 15 altogether of the actinoid elements in the F blocks of the periodic tables. All right, so at the bottom of the slide, you can see the 15 elements of the actinoids. You can use your own acronyms to memorize all the elements. So for the introduction, actinides are from F blocks element, as I said just now on the periodic table. Actinides are the 15 elements. We have altogether 15 with the atomic numbers starting from 89 to 103, which is it's filling up the F5 orbitals. The general electronic configuration of actinoids is F5 1 to 14, 6D, 0 to 1, and 7s2. Only actinium, thorium, protactinium, and uranium occur naturally, and most other are man-made. So in 50 elements of actinoids, not all are naturally occurred, but then most of them are man-made. Therefore, none of the actinoids have stable isotope because they are all radioactive. And the most longer-lived isotope in the actinoid elements, for example, neptunium-237, plutonium-242, thorium-232, and uranium-235, decay by alpha emission. Therefore, apart from being called actinoid elements, the International Union of Pure and Applied Chemistry, or IUPAC, prefers the term actinoids instead of actinides because the IDE from the actinides word is usually referred to reserved for negatively charged ions. All right, so I'm going to pass to Yasmin for further explanation of the properties of the actinoids.
Alright, thank you, Zaki. Okay, for the properties of actinides, first, all actinides are radioactive due to instability because they contain atomic number more than 83. So, in order to become more stable, the nucleus of the actinides will undergo radioactive decay. Then, they are highly electropositive. Electropositive means that the atoms tends to lose electrons and form positively charged ions. Then, they are malleable and ductile, means that the actinide metals are fairly soft. Then, they have the paramagnetic properties. Alright, so did you guys know why actinides have the paramagnetic properties?
Yes, yes, we know that.
Okay, why?
So from my understanding, it is paramagnetic. It has paramagnetic properties because it has unpaired electron in the F5 orbitals. Is that true?
Yep.
Yep, we can see that in their electronic configuration, right?
Yes.
They react with boiling water or dilute acid to release hydrogen gas. Form stable complexes with ligands such as chlorine, sulfate, carbonate, and acetate. And all these elements are silver-colored metals. They are solid at room temperature and pressure. And they are very dense metals with distinctive structures. They have numerous numbers of allotropes. For example, plutonium has 6 different allotropes. And lastly, the metals vanish readily in air. These elements are pyrophoric, means that they ignite spontaneously when exposed to air, particularly as finely divided powder. Next, I will pass this presentation to Aina.
Okay, thank you, Yasmin. So I'm going to proceed these presentations regarding the general trends of the actinoid. So the actinoids we do not exhibit any chemical uniformity. So since actinide is located in the F block in periodic table, so as Zaki mentioned below, the terminal electronic configurations of actinide element is radon 5F1 to 14, 60 0 to 1, and 7S2. So the energy of 5F and 60 electrons are close to each other, so electron will also enter into the 5F orbital. So 5F and 5D orbital also less compact than 4F and 5D orbitals, so them are more available for bonding. So for example, I take the electronic configurations for uranium. It's radon 5F3, 6D2, 7, and all 6 the most electrons are available for bonding. So, but however, this is only applicable for the early actinoids. So the actinoids beyond plutonium, which is like the images below, it only has 3 of the most electron readily ionized due to the post-screening by the other electrons. So we're going to go one by one regarding the general trends of actinoid. First, I'm going to talk about the atomic radius. So the atomic radius for actinide series is decreased regularly across the series. So this phenomenon of gradual decrease in atomic radius with an increasing in atomic number is what we call as actinide contraction. Okay, so for taking for example, how about Zaki? Can you tell us about, give me at least 2 examples regarding this increasing in atomic number but decreasing in atomic radius?
So, for example, atomic radius of the famous one, uranium 235, is 230 picometer, and its atomic number is 92. Next to uranium, we have neptunium, which is atomic radius is 200 picometer, while the atomic number is 93.
Yes, so you can see that there's actually a gradual decrease in atomic radius, but also an increase in atomic number. So this is what we call as actinide contractions, and it occurs due to the Poe shielding effect of the 5F electron. So Poe shielding effect, we know refers to a decrease in attraction the nucleus in an atom. So we also know that electrons are highly attracted to the nucleus. So when there is an additional electron in different orbital, so the electron will repel each other slightly. So this repulsion force will work against the nucleus attraction force and ultimately decrease the attraction between the electrons and the nucleus. So overall, 5F electrons have a very poor shielding effect because it is in a large distance from the nucleus. Okay, next point, we go for the melting and boiling point. So the actinides have a high melting and boiling point. However, as I said below, they do not show any regular trend with rising atomic number, and the melting point of actinide does not have a clear dependence on the number of electrons. So we know that melting and boiling point of actinide is high because of the size. So the lowest melting point is neptunium and plutonium, but it's also around 640 degrees Celsius. It's considered high, but it is the lowest in the actinide series. So next, we go for the metallic character. And so for the actinide, it is a typical metal, soft and silvery color. And as Jasmine mentioned earlier, it will be tarnished in air, and it will have a relatively high density and plasticity. So what is metallic character? Metallic character is referred to the reactivity of the metal. So it means that the easiness to lose the electron. So all actinides are highly reactive, but across the series, metallic character will decreases due to the decrease in an atomic radius. Okay, so for the other 3, electropositivity, electron affinity, and electronegativity, all 3 of these are related, but still we are going by one. So electropositivity is the tendency of an atom to donate electrons and form positively charged ion. So all actinide metals are highly electropositive due to the lower ionization energy. So we know the ionization energy can be defined as the amount of energy required to remove an electron from an isolated gaseous atom in its gaseous state. So I mentioned earlier that actinoids has poor shielding effect. So the electron can be easily removed from the atom, hence why it just needs a lower ionization energy. So next we go for the electron affinity. So electron affinity is the amount of energy released when an atom gains an electron. Actinides have a very little or no electron affinity as they are highly electropositive, meaning that they are preferred to donate or give electrons rather than accepting it. And lastly, we have an electronegativity. So since actinide possess a more complicated chemistry that does not generally follow any trends, therefore it does not have a standard electronegativity value. So that is all about general trends from me. I'm passing it back to Yasmin Diana for electronic spectra.
Alright, thank you, Ailina. Okay, for the electronic spectra of the actinides, for actinoids ion, the possible transition between electronic states only involve Laporte formula, which is F to F transitions, 5F to 6D transitions, and ligand to metal charge transfer (LNCT). By comparison with the latter nodes, the F to F transitions are broader and more intense due to the 5F orbitals have some interaction with the ligands because they are more spread orbitals than 4F, and the possibility of orbital mixing in 5F intensity of absorption is higher. Then, the bands for actinides ions are about 10 times sharper than latinides ions. Spectra of heavier actinides show more similarity with latinoids as compared to lighter actinides. Next. Then, lighter actinides complexes are colored, mainly due to the charge transfer and F to D transition. From left to right in the elements of actinides, the F to F transition is increasing, while the F to D transition is decreasing. The 5F to 6D bands are orbitally allowed, and therefore more intense than those of the F to F transitions. They are also usually broader and often observed in the ultraviolet region. Alright, this table shows the color and the spectral properties for the element of actinides. As you can see, they have different types of oxidation state, which is 3 plus, 4 plus, plus and 2 plus ions. It can be seen that they form different color depending on the oxidation state of the element. The table also shows the wavelength in the spectrum. The most with ligand to metal charge transfer transition. Ligand the unfilled orbital of the metal. As seen in the table, ligand to metal charge transfer transition result in the intense yellow color of the uranyl ion UO2 2 plus in solution and its compound. For neptunium 3 plus and plutonium 3 plus, the separation of the 5F and 6D level increases as the effective nuclear charge increases. Then, transition moves to higher energies into the UV region of the spectrum. Neptunium 3 plus solutions are violet and plutonium 3 plus solutions are light violet blue due to F2F transitions. The uranyl ion is also strongly fluorescent, with a strong emission between 500 and 515 nanometer when excited with UV radiation. So as you can see, figure 1 shows the emission spectrum of the uranyl ion excited with UV radiation. This property has been used for coloring glass, where the addition of 0.5 to 2% of uranyl salt produces a bright golden yellow color due to the charge transfer absorption. The glass has a bright green-yellow fluorescence in sunlight, which adds to its attractiveness. When viewed under UV radiation, it glows an intense green color.
So that's all from us. Thank you so much for listening.